G'day, in this video we're going to be unpacking the concepts of time dilation and length contraction. In this video we're going to be looking at dot point 7.4.2. We're looking at how light affects concepts of time, space and matter, particularly today, time and space. We've already started to look at Einstein's thought experiments and we're going to use them to try and figure out some quantitative relationships for time observed in different frames of reference. And so what we'll be talking about today is the idea that time can dilate for certain observers. And what we'll also note is that as a consequence, length can also contract. These shifts occur because of the constancy of the speed of light. So what we'll do first is derive the formula for time dilation and length contraction. We're also going to be talking about the idea of proper measurement, which is a feature of both equations. We'll talk about the Lorentz factor, which is essentially this element of the equation here, the big square root, and work on being able to account for time dilation and length contraction quantitatively. So in the previous lesson, we were having a look at Einstein's thought experiment in which he was traveling on a train, traveling at the speed of light, and he was shining a light at a mirror on the roof of the train. Inside the train, the observer will see the light hit the mirror, moving upwards, and hit the ground, moving downwards. Nothing too complex there. The reason that this is the case is because the person is in an inertial frame of reference, therefore cannot do any experiment to observe the fact that they are moving. Therefore, our regular understanding of physics applies as it usually would, as if we were stationary. However, for an external observer, they would see the light traveling in a diagonal direction because not only is the light moving upwards and downwards, but is also moving along with the train. These observations are very similar to what you would see if you were throwing a ball. The internal observer would observe the ball moving up and down, and the external observer would see the ball moving in a path akin to a projectile. However, what they would observe and measure is very different. In this scenario, both people would observe the ball exiting and entering the person's hand at the same time. And because the ball was moving at different distances, they would therefore calculate different velocities for the ball. However, for the light example, due to Maxwell's equation, the speed of light is constant, and this is one of Einstein's key postulates. If the speed of light is constant and the light travels across different distances, then what that must mean is that both observers see the light traveling over a different amount of time. Let's unpack that idea now. So in our diagram on the left, a diagonal arrow is showing what our external observer will see. However, we can break this up into some components. We've got in blue the light displacement that a person in the inertial frame of reference will see. We've got the red vector, which demonstrates the train displacing, and the diagonal vector, or the one that I'm drawing in black, as the displacement of the light that the external observer will see. And essentially that displacement is the vector sum of the blue and the red vector. What we can see here is that the light and the train are both displacing as time passes. Therefore, what we observe is different for the two observers. On the right, we've got a little bit of a redraw of our diagram here, which is just a little bit more cleaner and tidier, but this is what we're going to be using to be able to figure out how there is a difference in the measurement of time for the external and internal observer. And we know that V is equal to S on T, and that S displacement is equal to VT. As each of these vectors represent S, we can also rewrite the displacement as a product of the velocity and time. So the displacement of light as measured by the external observer will be based on the speed of light being multiplied by the time taken for the light to go from the bottom of the train to the top of the train as observed by the external observer. The displacement of the train is equal to the velocity of the train multiplied by the same time period, because this is also being measured by the external observer. However, I've written the displacement for light from the internal observer a little bit differently. Here I've written it as CT0. Why have I written it as T0? Because the internal observer has to measure a different time. T0 cannot be the same as T. That's geometrically impossible If we multiplied both values by the speed of light, we would find that both vectors were equal to each other in magnitude. This is clearly not the case. So given that the vector sum that we have here is a right-angled triangle, we can express the three displacements using Pythagoras' theorem. What that means is ct squared is equal to ct naught squared plus vt squared. This here is a mathematical relationship that is able to show that the observed time for the external and internal observer are different, but we can take it one step further and clean up the equation a little bit. In order to do that, I want you to imagine that you're the internal observer. How would your observed time compare to the external observer? So if we were to think about this quantitatively, what we are attempting to do is solve for t. So the first thing that we do is move all of the t terms to one side. The next step is to factorize for t squared. Then make t squared the subject. We can then clean up the right-hand side a little bit by dividing by c squared on both the numerator and the denominator. And then the last step is to square root both sides. And there we go. We have transformed our Pythagoras version of our equation that relates t naught and t and expressed it in the same way as you will find in your datasheet. This is the time dilation equation. Now this equation relates to times, one for each frame of reference. And this factor here implies that when we are applying special relativity, the two times which are measured are not equal to each other. And the difference between the two times will be dependent on the velocity of the fast-moving object. So when we're using our relativity formula, we're going to be required to use a proper measurement. And this is always taken from the rest frame of reference of the object which is being measured. So in our train scenario, the light was traveling in the train itself. And so what that means is if you're the observer inside the train watching the light, then you're considered to be at rest relative to the light because the light and you are both moving at the same speed. You're both in the same inertial frame of reference. Therefore, the person measuring the time for the light inside the train would be measuring the proper time, and the external observer who is not in the same inertial frame of reference as the light will be measuring the dilated time. If we were to invert the scenario, a person's traveling in a train, going really, really fast and watching someone outside the train. And let's say that they were shooting up a beam of light into a mirror above them, just like in the first example. In this scenario, the observer outside the train would measure the proper time because they're at rest relative to the light which is being shone outside the train, and the person in the train would measure the dilated time. So our time dilation equation, as well as the other equations for relativity, which we'll be looking at a little bit later, all include the Lorentz factor, which also may be written as gamma or referred to as the gamma constant. This essentially accounts for any relativistic dilation or contraction. And it is expressed as 1 over the square root of 1 minus v squared on c squared. As such, our time dilation equation can be written as T naught gamma. Our length contraction equation can be written as L is equal to L naught on gamma. And for a momentum dilation formula, PV can also be written as M naught V gamma. The table and graph over here demonstrate the idea that as an object gets faster and faster and faster, the Lorentz factor increases. As a result, this will exacerbate the dilation or contraction experienced between two observers in different reference frames. Why does that happen? Well, it all has to do with the idea that the ratio between the velocity of the object and the speed of light is getting closer and closer and closer to 1. As the value of this term here approaches 1, the square root here becomes a smaller and smaller number. And as that number gets smaller, the gamma value gets larger. And as such, when we are multiplying by those larger values, we get enhanced dilation or enhanced contraction. So when applying the Lorentz factor to time, what we'll find is that as velocity increases, the beta value will increase. The gamma value as a result will also increase, and therefore we will see an increased amount of time dilation. So let's have a look at a scenario where we can apply the time dilation equation. Here we have a rocket traveling past the Earth at 0.8 the speed of light, or 0.8 c. The time taken to travel between a blue and red marker is measured on both the rocket and as well from Earth. The observer on Earth measures the time to be 1.5 seconds to get from point to point, but in the question we're asked to calculate the time measured by the observer on the rocket. So in this scenario, the observer who is on the rocket is the internal observer. This means they'll be measuring the proper time, and the external observer will be measuring the dilated time. What this means is that the external observer should be measuring the larger time of the two. So when we calculate, we should be getting a T0 value which is less than 1.5. So from the question, what do we know? Well, we know the speed of the rocket. We haven't been given the exact speed as such, but rather we've been given the ratio of the speed as compared to the speed of light. As we saw in the previous slide, we can also call this beta. There's a little mathematical trick that we can use with beta to make solving our time dilation equation a little bit more simpler and straightforward. In most scenarios, you're going to be given this beta value in the question. So not the raw speed as such, but more a multiple of c instead. And we can actually substitute this directly into our equation, even though beta isn't in the equation that's in your data sheet. The part that's in the data sheet that we're most concerned with here is the v square on c square part. This is equal to v on c square. So if v on c is beta, then v on c square is essentially beta square. And that's what we actually want to sub into our formula. So in this case, beta square is equal to 0.8 squared. And we can sub that straight in. The other information that we've been given is t, and that t is equal to 1.5 seconds. So despite the formula being quite complex, the solution is fairly simple. All we need to do is make t0 the subject. And to do that, I'm going to multiply the denominator on the right-hand side up to the left-hand side. From here, all we need to do is substitute. And when you put that into your calculator, you should get 0.90 seconds. Noting here that because we should be getting a smaller time as we predicted, because 1.5 seconds is the dilated time, a result of 0.9 seconds seems completely reasonable. So now that we have an equation for time dilation and proved that we can use it, where does this length contraction equation come from? Well, the two equations are quite closely interlinked. And the reason is it comes all the way back to this idea that v is equal to s on t. That means that velocity, displacement, or in this case, length and time are all very closely related. Let's try and derive the length contraction equation using our rocket scenario that we just worked with. If we have two observers and they agree on their measurement of velocity, that's because the speed of light is constant as based on Maxwell's work, but they disagree on the measured time because of time dilation, then their measured results for distance must also be different. What that means is that the person on the rocket and the person on Earth measure the distance between the blue and red marker differently. Let's see if we can demonstrate this relationship. Now, interestingly, for the external observer, they're actually going to measure the proper length this time because they are in the same reference frame as the two markers. Unlike the rocket, they're not speeding past them. And for the rocket and the person inside it, because they are moving past the markers at a speed approaching the speed of light, they are going to be measuring the contracted length. So to quantify, the velocity measured by the internal observer is going to be the length measured by the internal observer divided by the time measured by the internal observer. And because both observers agree on the measurement of the velocity, that also means that this measured velocity is going to be equal to the length measured by the external observer divided by the time measured by the external observer. We can quite easily rearrange this formula to make the length measured by the internal observer the subject. At this point, I want to be able to remove the time terms from the equation and just have an equation that involves length only. What I also want to be able to do is introduce the Lorentz factor as well. To do that, I'm going to need my time dilation formula. I'm going to write that as T is equal to T naught gamma, where gamma is our Lorentz factor, 1 on the square root of 1 minus v squared on c squared. And in the previous example, we said that the dilated time would be measured by the external observer, and the proper time would be measured by the internal observer. What we can do from here with these two equations is substitute in the second into the first. At this point, we've removed TE, and quite conveniently, TI gets cancelled out. This leaves us with the length of the internal observer being equal to the length measured by the external observer divided by gamma. From here, I'm going to rewrite gamma as 1 on the square root of 1 minus v squared on c squared. When we divide by 1 on the square root of 1 minus v squared on c squared, that's actually the same as multiplying by the square root instead. And in the last step, all I'm doing is stating that the length measured by the internal observer is the contracted length, and the length measured by the external observer is the proper length. And we'll find that this formula that we have matches up with the one which is in your data sheet. So let's have a go at applying the Lorentz factor to length. The key question that I want to ask here is, what length do the observers actually measure? We know that they both measure the velocity of the rocket to be 0.8 c, which is 2.4 times 10 to the 8 meters per second. We know that the external observer measures a dilated time of 1.5 seconds, and the internal observer measures the proper time to be 0.9 seconds. From here, we can just use our speed equals distance over time formula to be able to calculate for what their measured lengths would be. And as we can see, the external observer would measure the distance to be 3.6 times 10 to the 8 meters, but the internal observer thinks that the rocket has only traveled 2.16 times 10 to the 8 meters. This is a contracted length. What we should be able to demonstrate now is that the equation for length contraction holds based on these calculated measurements that we've determined based on the proper and dilated times already accounted for. So by substituting in our proper length as well as the speed of the rocket, we can calculate that the expected contracted length is exactly equal to the contracted length that we just previously calculated, which was 2.16 times 10 to the 8 meters, thus demonstrating the interconnectedness between the time dilation and length contraction formula. So just to wrap up, there are two key concepts that are really important here that explain how this problem is solved. First is that the length being measured here is external to the rocket. Therefore, the Earth observer is stationary relative to the markers. Therefore, they measure the proper length. And therefore, the contracted length is calculated for what the internal observer in the rocket observes. Another way of thinking about this is that if a smaller time interval is measured on the rocket therefore must travel through a contracted distance to make sure that the measured velocity of the rocket in the internal frame of reference is the same as the velocity of the rocket measured by the person in the external frame of reference. Thank you very much, everyone. In the next video, we're going to start to unpack some of the evidence that exists for time dilation and length contraction. But until then, have a good one.